We're off. Okay. So we're going to try to graph some polar curves, see how far we can get without the technology. And we're going to start with number 12 from the homework, which is r equals 3 plus 3 cosine theta. Okay? Now looking at this graph from the homework, which general form does this equation seem to take? We're looking at a rose, a lemniscate, a limacon, a cardioid, a spiral. What do you think we're looking at? Limacon, which we're all going to pronounce very horribly, unfortunately. I think so.
Yeah, it's got the little.
Yeah. Okay, so in this case, we have A is equal to 3 and B is equal to 3. Now, I always like to make my table, and let's see how this plays out, see if we can get some hints from a table. Now, what I told you guys yesterday was the points I like to think about on my table are the 4 points of the compass all the way around plus 360. So 0 radians, pi over 2, pi, 3 pi over 2, and 2 pi. The exception to this I did in the example was if we have a coefficient in front of the theta. Anyone see a coefficient in front of the theta? No. Okay, so we're going to put 0 radians in for theta. And what is the cosine of 0 radians? 1. Good. So this is going to be 3 plus 3 times 1. So at 0, we have a 6. Okay? Pi over 2. What's the cosine of pi over 2?
1.
Cosine of pi over cosine of 90 degrees?
0.
0. 3 plus 3 times 0, so that's just going to be 3. At pi, what have we got going on? What's cosine of pi? Cosine of pi is -1. Andrew is remembering his unit circle. Ike, redeem yourself. What's 3 plus 3 times -1? 0. Good. Don't overthink that one. At 3 pi over 2, we also have a cosine of 0. So again, it's just 3. And at 2 pi, we're back to 3 plus 3 times 1. Yeah, get a cosine of 1 times 3 plus 3. We have 6. All right, so let's graph these points. Let's see what we're looking at. These are my polar axes. So that's 0. That's pi over 2. That's pi. That's 3 pi over 2. So when we're facing 0 degrees, we go positive 6. When we're facing pi over 2, 90 degrees, we go to 3. When we're facing pi, we don't go anywhere, we go 0. At 3 pi over 2, 270, we're also 3 units away from the origin. Now, this can be confusing. In Cartesian terms, this would be 0, -3, but this is still positive 3. This is 3 pi over 2, comma, positive 3, because we're 3 positive units away from the origin. So what we have is a radius, a distance from the origin, that at 0 radians starts at 6, shrinks to 3. As we get past 90 degrees, between 90 degrees and 180, this radius has to shrink to 0. Then it starts to grow again, out to 3, and the radius keeps increasing back to 370 until we get to back to 6. So that is the classic cardioid. So you weren't wrong when you said limacon over here, Ike, but a more specific case of the limacon is when A and A are the same number. Instead of A and B, 2 different numbers, we had A equal to 3 and B equal to 3. That's your cardioid. That's what it looks like. Any questions on graphing that one? I always like to make my 4 points of the compass, well, 5. I do go all the way to 2 pi just to double check, and then see how it fits, how that helps me with these. Any questions on that polar graph? Nope. All right, so the next one I saw was number 14. What's that look like? What's that one say? All right, so now we are going to graph this lemniscate r squared equals 4 cosine 2 theta. I know, it's a shocking new development that we've never attempted before. not in any way, shape, or form. And when you have a coefficient in front of the theta, you do things a little bit differently. I still like to check my 4 points of the compass on there. I already have the lemniscate up here, but let's rediscover it. I still like to check my east, north, west, south, east again. But when you have a coefficient in front of the theta, you don't plug in 0, pi over 2, pi, 3 pi over 2, 2 pi. It's much easier to plug in the angles after you divide these by that coefficient. So 0 divided by 2 is 0. Pi over 2 divided by that coefficient is, gentlemen?
What?
Pi over 2 divided by that coefficient gets you?
Pi over 4.
Pi over 4, thank you. Okay, stay with us. Pi divided by 2 gets us
Pi over 2.
pi over 2. 3 pi over 2 divided by that coefficient gets us
Pi over 4.
3 pi over 4, and 2 pi divided by 2, I'll give you that one, gets you pi. Okay, now, the difference here, which can be confusing and easy to do backwards, is that when you plug in a 0, you don't get an r, you get an r squared. So you put in cosine of 0, even when you double it, is still 1. 1 times 4 is 4. That is our r squared. The square root of 4 is 2. So if r squared is 4, r is 2. We plug in pi over 4. You double the pi over 4, you get pi over 2. The cosine of pi over 2 is 0. R squared is 0. R is also 0. Here's what causes a lemniscate to not exist for 50% of the way around the circle. You put in pi over 2, it gets doubled. Then you're finding the cosine of pi. The cosine of pi is negative 1. 4 times that is negative 4. If r squared is negative 4, then r has no real solutions. And at least for today, we're not going to talk about I and imaginary numbers, complex numbers on polar coordinates. So this thing stops existing in the real number plane when you get to 90 degrees. It's done. At 3 pi over 4, down here, that gets doubled. 3 pi over 2, 270. Cosine is again 0. And when we get out to plug in pi, it gets doubled to 2 pi. We once again get a cosine of 1. 4 times 1 is 4. Square root of 4 is 2. So this gives us a radius of 2 at 0. By the time we get to pi over 4, this radius of 2 has shrunk to a radius of 0. Then it doesn't exist for a while. We get to 3 pi over 4. It starts existing again, goes out to 2, and it will continue until it finishes that shape. And that's where a lemniscate comes from, if you have to graph it without a calculator, which you will. Any questions on that one? Nope. Okay. There's a slight difference if it's a sine. If your lemniscate is r squared equals, let's say 4 sine squared sine 2 theta, here's what happens instead. If you're looking at sine 2 theta, the sine of 0 degrees or radians is 0. This lemniscate is going to be rotated, interestingly. What happens to it is when you get to pi over 4, you put in pi over 4, that's where this peaks. Take pi over 4, double it, what do you get? Pi over 2, good. What's the sine of pi over 2? 1. So the sine, very good. So that's where you're going to hit your peak point. So a lemniscate with a sine in it hits its peaks at pi over 4 and down here at 5 pi over 4. So the only difference between a cosine, a lemniscate with a cosine in it is going to be along the horizontal axis. A lemniscate with a sine in it is going to start at 45 degrees and have the same basic shape. Does that make sense?
What would be vertical?
Vertical, the easiest way to get vertical would be to add a rotation. Remember how we did the K and H motions of sliding around with functions, moving things left and right, up and down? What you would do is, to make it vertical, I would take r squared equals 4 sine 2. I would say theta plus pi over 4, because instead of sliding things left and right, when you add an angle inside the function with theta, it rotates your polar function.
So then why do you need sine and cosine functions for that if you just rotate one?
You don't. Remember, it's the same. I think you asked a similar question when we did sine and cosine waves. They're the same wave, just shifted left and right. You can always express a sine as a cosine or vice versa. Sometimes it's just more convenient. There's other uses, but if your only goal in life is to draw lemniscates, you could pick one or the other and rotate them. You would not have to deal with those. There are other advantages. Okay, so that's a lemniscate. Any questions on that one? Nope. Okay.
Is that how you would graph an oval if it was if you set it only in the positive quadrant?
Hold that thought. All right. Let's take a look at this one. Looking at these classical curves over here, which one am I looking at with this negative 2 sine 3 theta? What type of shape is this? This is a rose. All right, let's see what kind of rose this is. I'm going to do my theta r table. I'm going to put my 0, pi over 2, pi, 3 pi over 2, and 2 pi radians over here in red. Why am I doing this? Why am I not just putting them into my theta column?
Maybe we have to modify it.
Yeah, 3 up there.
I want to modify these for best results. Very good. So I'm going to divide them all by 3. So I'm actually going to look at 0 over 3, pi over 6, pi over 3.
Wait, not r squared.
No, but it's not r squared because it's not a lemniscate. Only lemniscates have the r squared. Good eye, keep looking for that. Everything else has r. One way to look at it, and this would be 2 pi over 3. One way to look at it is, it's kind of like thinking in terms of functions. You know how your calculator, you weren't here yesterday. You know how your calculator will only let you graph r equals.
Yeah.
It won't let you graph a lemniscate. It's kind of like your calculator will only let you graph y equals. For polar functions, you can't really think in terms of a vertical line test because everything we've done would fail it. But if you see r equals, it's a polar function. It's a little easier. Think of it as being like a function. You see the r squared, you're looking at something a little different. For instance, your calculator couldn't graph that. There's a trick around that, but maybe I'll show you guys that trick later. Okay, put 0 in for theta, triple it, you still have 0. What's the sign of 0? 0, so that's just going to be 0. That one's easy. Okay, put pi over 6 in for theta. We triple it, it's pi over 2. What's the sign of pi over 2? 1. -2. Andrew's been studying his unit circle, I love it. Put pi over 3 in for theta. Triple it, it's like putting pi in for theta. What's the sign of pi? 0. Put pi over 2 in, it gets tripled to 3 pi over 2. Sine of 3 pi over 2, 270 degrees, as far south as you can go. -1. -1 times -2 is +2. And we put 2 pi over 3 in, we triple it, we get 2 pi, we get 0 again. Now, this makes it easier to calculate by using these values, but remember, we actually are using these angles. This is where these points occur. So, at 0 degrees, nothing's happening. At pi over 6, 30 degrees, that's something like that. We are out at, whoops, oh wait, which way do I go? Do I go into quadrant 1? I mean, 30 degrees is quadrant 1, right? Yeah, but which way do I go? Into which quadrant I go? And why do I do that? Excellent. A negative radius means go in the opposite direction. Okay, you missed that yesterday, but I'm sure I think it was on one of the pictures we sent you from the board. Okay, so negative radius means go in the opposite direction, so at 30 degrees, I'm down here. At 60 degrees, I'm back to 0. At 90 degrees, I'm up here at 2. And at 2 pi over 3, I'm back down to 0. So let's see, we've got these negative radiuses down here, radii. I think that's the whole function. I think that's it. Missing 1.5 leaves. Yeah, this thing would have to go around more times. But there is a sort of symmetry to this. I'm not drawing these lengths very well. These lengths are all supposed to be, do a better job on that one. These lengths are all supposed to be 2 units from the origin. So this is the point 2 comma pi over 2. This is the point negative 2 comma pi over 6. We can also label this point as positive 2 comma 7 pi over 6, but this is more in keeping with what we got from there. And this one over here, I'm just going to label it the simple way. This is 2. Okay. These have to be these rose petals have to be evenly spaced. So how many degrees apart are they? 360 divided by 3, 120. Okay, so if we start up here at 90, then plus 120, we must be going down to. Does that work? Yeah. So that's.
I mean, with that pattern, once you got past 720, wouldn't it just be another cycle of the same thing?
Yes, absolutely. Would it keep repeating forever? That's why when we did this on the calculator yesterday, like with parametric equations, we did a T-min and a T-max. We have a theta-min and a theta-max on the calculator now. So you pick how many times you want it to go around. Okay, so here, plus 120, where am I winding up? From 7 pi over 6 plus another 120 degrees.
That would be 180 times 1 over 6 plus 1.
210. It's 7 times pi over 6, which is 30. All right, so that's 210 plus 120. That gets you to 330, right?
Yeah.
Okay. So 330, I like to think of this as 11 times 30 degrees, because then that way it's 11 times pi over 6, since I always remember pi over 6 is 30 degrees. So that's the rose. With a 3, you get 3 petals. What do you think happens with a 4? That would make sense, but you weren't here yesterday. Yeah, no, it's actually double. You get 8 petals, which we have over here, which you know what you see in the video. No, double.
3 times 2.
Okay, I'm sorry. I said that wrong. If you had 4 petals, let's try this again. If you have a coefficient of 4, you will get 8 petals. If you have a coefficient of 5, you'll get 5 petals. If you have a coefficient of 6, you'll get 12 petals. So the pattern for the petals is an even coefficient, you get double the number of petals. An odd one, you get the same number of petals. That's the pattern for the rose. Okay? We got to a cardioid, we didn't get to a lemison, it wasn't a cardioid. We got to a lemniscate, we did 1 rose. All right, we will, next period we will do a couple more of these. Any quick questions on this one? All right.